Boom. Hello and welcome back to Trig Review. So we're talking about trig equations. This is a very important topic as these equations are solved frequently, not just in calculus, but also in sciences, physics, and so on. So, first of all, expressions connected with the equal sign, where you can compute the variable, are called equations. One of the most basic equations, let's say x plus 2 is equal to 5, right? And then you know the way to solve this. You would use the additive inverse, which is opposite operation. You have x plus 2, and then you are going to subtract 2 on both sides and get x equals to 3. Now, the more important part here is its graphical representation. You can solve this equation graphically with the right amount of OCD. So you graph the line on the left side, which is x plus 2. So it has the y-intercept of 2 and the slope 1. And then on the right-hand side, you have 5. So this equation is f equals x plus 2, and this equation is g equals to 5. So these are the two functions. And as you can see, they intersect here at the point 3, 5. Well, from there you can clearly see that x is 3. Every equation can be solved graphically if you graph the left-hand side of the equation as a function, the right-hand side of the equation as a function, and if those two lines intersect, then you guys have the what do you call it? The solution. So intersection is a solution. And we see that they intersect at x equals to 3, right, on x-axis, x equals to 3, so, and that was a solution, right? So we're good there. Every equation can be solved this way. So we have these two notions. One notion is that you will use the opposite operation to peel off everything and leave x alone, or you can do it graphically. Right? Now, the trick is that, you know, graphically it's very tedious. It's kind of hard to read from the graph, you know, the precision and all that kind of stuff. So we would like to do it analytically, meaning calculations, computations. So we would like to use that instead. Now, if I have sine of x is equal to 1/2, I'm supposed to solve this equation. And you are used to having x equals 3, x equals the half, x equals to all these kind of things. Well, the issue now is that we are going to have multiple solutions. And if we don't restrict the domain, we are going to have infinitely many solutions. Think of the sine wave, which is not restricted in any way. You remember the way that sine will forever go on? So we have this sine wave which will forever do this. Now I have to draw at least one on the other side. I don't think it can fit over here. And so on. And we know that in the range, sine goes between -1 and 1. And it has infinite domain. Now, this is the graph of the left-hand side. Now, let me graph the right-hand side. It's a half. You see this? Boom, 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 boom. All blue points are solutions. There are infinitely many solutions. Sine x equals 1/2 has infinitely many solutions. Now clearly, if I limit my sine graph from 0 to 2 pi, I'm going to have two solutions only. I have two blue dots on 0 to 2 pi. But if I do not limit this, I have infinitely many. And we have mathematical representation for restricted domains and for the entire thing. So the blue points are the solutions, and I'll say on negative infinity to infinity domain, we have infinity of solutions. On 0 to 2 pi domain, we have two solutions. And now you might say, okay, so that's all cool to understand, looking at the graph, right? Having a flashback to what you did ages ago, right? For equations. But now you might say, so how do I solve this analytically, right? No graphs. The graphs are good to understand and visualize the number of solutions and all that good stuff. So we have sine x is equal to 1/2. Now remember what you did earlier, x plus 2 equals to 5. You subtracted 2 because that is the opposite. It is removing the stuff that is hindering you from having x alone. Now what's happening here? Well, you have sine in front of x, and you need to get rid of it. The way to get rid of the sine is to hit it with the inverse sine on both sides. And now these guys kill each other. And what you get is x equals sine inverse of 1/2. And now you are going to look at the chart. So look at the chart, right? Remember the chart of all the values that we dealt with. And you find that x is equal to pi over 6 or 30 degrees, whatever, right? But pi over 6 is better, right? Now you know that the story doesn't end there, because you found 1. On 0 to 2 pi you have two solutions, and on the entire domain you have infinitely many solutions. You found 1, right? So the goal is to find the other solution. To find the other solution, should I say quickly, efficiently, whatever? If you look at the unit circle, this point here is 0, 1, and this point here is 1/2, right? So this is where pi over 6 is. All students take calculus. Sine is also positive because this was sine x equals positive 1/2. Sine is also positive in the second quadrant. So this point is your other solution, right, when you reflect. So that one is 5 pi over 6 because the next stop is pi, which is 6 pi over 6. So, using unit circle, we get that the second solution is 5 pi over 6. Great. Now, does that make sense on our graph up there? Hell yes. Here's your 5 pi over 6. Here's your 5 pi over 6. Then here is pi. And pi is 6 pi over 6. Oh, come on. Yes. Let's wait a second. The software exploded. I think it's back. Yep. Now I have to fill this in. So blue ones. That's the y, that's the 1, that's the 1/2. That's pi over 6. There we go. I hope that the rest of the stuff is still there. Yep. Very good. Your x-axis is now partitioned in terms of pi. So for sine 0 to pi to 2 pi. There's a pi over 2 in the middle. And you can see that these are thirds now, because a third of a pi over 2 is pi over 6, because pi over 2 times 1/3 is pi over 6. So all of the partitioning looks good. We have these partitions that all make sense. You see 6 divisions there, and you count in pi over 6s to end with 6 pi over 6 at pi, because 6 and 6 would cancel. So to solve an equation sine x equals positive 1/2, you will apply inverse sine to both sides, and then you would look in your chart that you have from before, and you see that sine of 30 is 1/2, which means that the inverse sine of 1/2 is 30 degrees, which is pi over 6. Which gives you one solution. Oh, this is the whole bunch of stuff missing here now. Let me just fill this in again. Alright, should be good. So now let's solve the same problem, but this time sine x equals negative 1/2. So now it's negative. Alright. I'm going to write this sine x equals and then leave some space to apply my inverse sine, because inverse sine is the one that kills off the sine. And what we are left with is that we have that x is equal to sine inverse of negative 1/2. Great. We are going to immediately draw the circle. I'll draw a little bit bigger. So we have this. And now the question is, where is the negative 1/2? Well, negative 1/2 is here, right? Because this is 0 and this is negative 1. So negative 1/2 is this elevation, which means we have this angle and this angle. Now we know that 1/2 is related to pi over 6. So this puppy better be 1 pi over 6 more than 6 pi over 6, which is 7 pi over 6. And this one over here is 1 less than 12 pi over 6, which is 11 pi over 6, as you look. Observe also that all students take calculus fits perfectly, because we were looking for a negative sign, and that's in the bottom 2 quadrants. Sine is positive in quadrants 1 and 2. It's negative in quadrants 3 and 4. So all of it at once. It works, all of it works at once. The negative 1/2 is the line that it's below x-axis on the negative half, y equals negative half. All students take calculus T and C, signs are negative on those. So all of it kind of gets together and we get it. So now x is equal to 7 pi over 6 and also 11 pi over 6. Now this is just on 0 to 2 pi. I'm not talking about infinite solutions yet, infinite number of solutions. This is just the principal period, right, the first one. Let's solve a tad spicier equation. Say cosine x is equal to negative square root of 3 over 2. All right, that's what I want to do. Well, cosine x is equal to, and I leave some space to apply my inverse cosine. Now, the inverse cosine will kill off the cosine, and I have x equals to inverse cosine of negative root 3 over 2. Now, root 3 over 2 and a cosine, that works with pi over 6. But I have to see what pi over 6, where, and what's the other one. So we draw the unit circle. All students take calculus, and we see that the cosine is negative in the quadrant 2 and quadrant 3. I know that just by looking at the equation, because I have a lot of experience here, obviously, but when I see the equation, I say cosine is negative, right? Because that's what the question, I don't care what number, is it root 2 over 2, root 3 over 2, or whatever, blah. Is it positive or negative? That's the first thing I look at. It's a cosine and it's negative, which means solutions are going to live in second and the third quadrant. Solution is cosine is positive, it's first and fourth. So the sign here immediately determines which two quadrants you're going to have a solution to. And then we jump to see the numerical value of that solution, and a cosine root 3 over 2, that's pi over 6 again. So now we have pi over 6 so cosine root 3 over 2 to give you root 3 over 2 is pi over 6. So we have these two. Five pi over 6 and 7 pi over 6. Those are the ones. Again, on 0 to 2 pi. Let's try tangent of x equals, let's say, positive root 3. Tangent of x equals positive root 3. Positive implies quadrants 1 and 3 for tangent. Tangent right? When you do all students take calculus, tangent is positive in quadrants 1 and 3. To get the numerical value, we again write tangent is equal to, leave some space, so we can fit in the inverse tangent on both sides. These guys will cancel, giving me x equals tangent inverse of root 3. Now, we know that tangent inverse of root 3 is going to give us pi over 3. But I have to work out my quadrants. So, unit circle, get our quadrants going. And by all students take calculus, I know that I have to be in the first and the second. Now, pi over 3 in the first. And then, extending the line, it's pi over 3 on the other one. So this is pi over 3. And this is 4 pi over 3. Now, remember the reference angle? This puppy is pi over 3. And this puppy is pi over 3. So those are reference angles for both. And if you go back to each one of these solutions, the reference angle was always what you find from the chart of basic values. You see pi over 6, pi over 6. Yeah, the solutions were 5 pi over 6 and 7 pi over 6. But the reference angle was pi over 6 going up and going down, because that is what inverse cosine of root 3 over 2 is. It's pi over 6. But then you have to put that in a quadrant where you have to be. So for tangent now, we start with a positive. Positive is first and the third quadrant, and then we go and figure out that it's pi over 3. So now I know that the solution is pi over 3, comma, 4 pi over 3. So we have two solutions, again, on 0 to 2 pi. So that is our basic. So these are the basics, obviously, because soon we are going to have this married with trig identities, married with the double angle and triple angle and all of that kind of stuff, which multiplies the amount of answers present. So let's talk about infinite solutions. I am going back to sine x equals 1/2, where we found that x is equal to pi over 6 and also 5 pi over 6 with the graph which looked like this. Now, I want to make sure that you understand that I have to draw that introductory graph. That's one. Negative one. I know I'm not drawing this to scale, but at least we'll have a nice wave going. All right, so And then I'm going to hit the, let's go blue, 1/2. The intersection is pi over 6 and 5 pi over 6. But then there is another one over here and here. Now here's the cool thing. Observe that the next one happens at 13 pi over 6. And then this one at 17 pi over 6. Now I need to make sure that you understand that if I go pi over 6 and this one, there's a 2 pi between them, which is a period. And if I go with the purple here and here, there's also 2 pi in between them. If I'm to go negative to these two solutions here, this one would be negative 11 pi over 6, and this one over here would be negative 7 pi over 6. And with the black and purple lines, we get the same thing. There is always, these come in pairs. So pi over 6 is going to give all of the answers, infinitely many of them, if you go period, another period, another period, another period to the right, and then minus a period, minus a period, minus a period to the left, forever. Now we can compress this into a single answer. So all of these black answers, no, that's purple answers. All of the black answers are going to start at pi over 6, and they're going to add and subtract 2n pi, where n is 0, 1, 2, 3, 4, 5, and so on. Observe what this does. When n is 0, this term is gone, and you just have your basic pi over 6 solution. When n is equal to 1, you use pi over 6 plus 2 pi, and that's this solution. If n is equal to 1 and you use the minus, you get pi over 6 minus 2 pi, and that will be this solution. You can jump to any solution. This. You want to be computer science? This is what you read and breathe every day. This is what computer science looks like. All right? This discrete jumps. There's no continuous. Everything is discrete, computer science. So I am able to capture infinity of discrete solutions in this one statement where I say the principal solution on 0 to 2 pi is pi over 6, and then I have infinity of other solutions by simply adding or subtracting 2 pi, 4 pi, 6 pi, whatever I need, and these are the counters. And now I have a purple solution where I write the same thing off of pi over 6, 5 pi over 6. So x is also equal to 5 pi over 6 plus minus 2n pi, where n is equal to 0, 1. I don't have to write this n. It's the same n for both. And together, so this is the solution. Now, clearly, you will write this n just once. You can go back now and write for all of your previous problems. You can go back and write all the infinite solutions. And they all work the same. Well, tangent is nicer because their period is pi. So actually, you can squeeze by writing one solution. Who wants to study electrical engineering now? Yeah? No. Now, this is the basic case. Can we make this interesting? Sure. I can make, instead of having 2 solutions, I can make 3 or 6 basic solutions and then plus 2n pi on each one of them. It's still going to be infinitely many, obviously, but right. So, as you can see, you compute the principal ones, and then it's principal plus a period or principal minus a period, which is this plus minus. This is the period, 2 pi, and then n is the counter. That which solution do you want? I want the 5th solution to the right. Oh, great, 5th solution to the right. This is the first. So 1, 2, 3, 4, 5. This is the 5th solution. So plus 8 pi, 8 pi is 48, 49 pi over 6. Done. Right, 49 pi over 6. So you can find any solution you want as far as you want to go out, right, to find it. And then again, this is an infinite wave. Goes on cascading forever. Good. Let's solve some of the problems from the textbook. And then we'll move to the spicier cases. First, we're going to do this easier, faster. So, problem 20. Oh, come on. Problem 20 says, this is 5.5, problem 20. 2 sine x plus root 3 equal to 0. All right. Move root 3 to the other side. So that's a negative root 3. Divide both sides by 2. And we have something to work with. So now what do we know? If I am to apply inverse sine on both sides, I also see negative and sine. So together that means quadrants 3 and 4, because sine is negative in quadrants 3 and 4. And the inverse sine of a sine and root 3 over 2 work with pi over 3, or the 60 degrees. So that's my reference angle. With all of this information, we compile the units. I don't want you to be blue. So with all of this information, we first figure out where this stuff is. So this is my unit circle. Pi over 3 in quadrant 3 is here, because I need pi over 3 reference angle. And then in quadrant 4 is here, because that's pi over 3 reference angle, and that's pi over 3 reference angle. Now the actual answers that you are getting are 4 pi over 3, because remember, this is pi, and pi is 3 pi over 3, so this is the next one. And then 5 pi over 3 is the next one. And then it's a 2 pi on this side, which is 6 pi over 3, which is 2 pi. So 3, 4, 5, 6. They fit. 3, 4, 5, 6. The red ones are reference angles, which we are getting from the chart of values where the sine is connected to root 3 over 2 and the 60 degrees or pi over 3. So now, what are my solutions? The first solution is 4 pi over 3 plus minus 2n pi, the period. The second solution is 5 pi over 3 plus minus 2n pi, and n is 0, 1, 2, 3, 4, 5, 6, 7, whatever, and that's the solution. So infinitely many solutions. Again, it's very structured, but you just have to know all of the components of it. Now, it might be overwhelming now because you either don't remember, or you have to practice more, or whatever. But when I am at the state when the trig function is equal to a number, I look at that number. Is it positive or negative? Okay, it's negative, and it's sine. Negative number and the sign from all students take calculus, quadrant 3 and 4. So my principal answers are in quadrant 3 and 4. Now, what is the value of those answers? Well, the root 3 over 2 and the sign in the chart work out to be 60 degrees or pi over 3. Great. Reference angle is pi over 3. So, in the quadrant 3, what's pi over 3 from x-axis? Well, it's here. So, that's the one. And what's its value? Well, if this is 3 pi over 3, then the next one, right? 1 pi over 3 later. So 3 pi over 3, 4 pi over 3. Walk away from that one. This is the quadrant 4, where we are supposed to have a second solution, again, because it was negative in sign. So pi over 3 to the closest x-axis is here. This is 6 pi over 3 minus pi over 3 is 5 pi over 3. Great. Remember that the negative limit comes this way, so minus pi over 3. So check for common sense. 3 pi over 3, 4 pi over 3, 5 pi over 3, 6 pi over 3. Good. I have 1, 2, 3. 1, 2, 3. 3 pi over 3. That's good, because there's a pi in between. So it all fits together at once. This is the first solution, plus minus the period, depending on n. You want to go back or forward. And then the second solution, 5 pi over 3 plus minus, again, the period with the n, to give us all of the solutions that way. Cool, huh? Yeah, I should take a group picture now with all of you being fairly disappointed in life, right? Well, let's make it spicy. We are going to change the period. We are going to change the period now, which will change the amount of principal solutions. The amount of principal solutions in the basic case was 2 on 0 to 2 pi. You've seen it for sine and cosine. and tangent had it as well. But now, what happens when I say sine 2x is equal to 1/2? Sine 2x makes the wave faster. And if the wave is faster, from 0 to 2 pi, it's going to draw sine twice, changing the number of solutions from 2 to 4. So graphing and everything else, right, if you want to really have the understanding of all of this stuff, it really changes. So if I go and say sine of 2x equals 1/2 now, so this problem is different. Now sine 2x, if you remember, I said it already, the sine is going to be twice as fast. I'm just going to draw a little bit of it. So these are the standard tick marks, this one being 2 pi where it ends, and it used to go here, so now it's going to go here, and then here, and then here, and then here, and then here, 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 and back. And as you can see, it's traveling twice as fast, intersected with the line 1/2. We get 4 solutions. So we are expecting 4 solutions. Expecting 4 solutions on 0 to 2 pi. Because the sine was twice as fast, it completed 2 full oscillations from 0 to 2 pi. Therefore, we are expecting 4 solutions with a 1/2, right, intersection. So that's a 1 and it's a 1/2. All right. Let's try and find them. We know the drill. Sine 2x is equal to 1/2, and then we hit both sides with the inverse sine. What you get now is that the 2x is equal to pi over 6. See that? Because inverse sine kills off the sine, but what's left behind is now 2x. And yes, you have to multiply both sides by 1/2 to get x equals pi over 12. Aha! The first solution here is pi over 12. Now, what's the new period? Is it pi? Is it 2 pi? What is the formula to calculate period from Friday? For graphing. P equals two pi over B. So the new period is pi. Aha. So the next one, which is this one over here, right? That solution is going to be pi over 12 plus pi. And that is 13 pi over 12. Okay. So now we have those two. Now what am I going to do for the other two? So these are the first two solutions. Oh, come on. So now, to find the other solution, we go back to the 2x case, and in the unit circle, right, we know that the positive sign is on the other side, right here. So pi over 6 was used for the first solution. Now 5 pi over 6 is going to be used for the second solution, so 5 pi over 6 is the second one. Again, divide by 2, 5 pi over 12, comma, 5 pi over 12 plus pi, the new period, gives you 17 pi over 12. So maybe I should somehow, let's do this. So pi over 6 is that one, and 5 pi over 6 is this one. So we still use the basic solutions, ignoring the 2x case, and then we deal with the 2x. So when you take off the sign, whatever is here, could be 3x, could be 17x, it doesn't matter. Those answers are going to be the good old answers, and then we have to divide both sides by 2, giving you pi over 12. And then plus period, because we are expecting 4 solutions. We're going to do one with 3 as well. Just in case. I don't think that they would go on the test. Like, I think this would be the craziest amount of calculations. But again, it's not just about the test. I mean, you can pass the test, then what? Right? If you don't know this stuff, you're sitting in Calc 1 and just like, yeah. Because you're supposed to know this, right? Going into Calc 1. I can't sit and explain this when I'm calculating critical points in Chapter 4. Calc 1, I can't be sitting and teaching you how to do the equation. And you open a calculus book and this equation is there. So, you know. And you solve the sign for, let's say, you solve sine 2x equals whatever for the inflection points, and then you have to solve the cosine of 2x in the same problem. Cosine 2x for the inflection points, which is on the second part. So, you know, this stuff just needs to make sense and practice and know in order for it to work well. One more equation. This time I want to use 3. Let's see what they have. Oh. Problem 30. Tangent 3x equals root 3. Done. Cool. I immediately copy the problem and leave the space for the inverse, and then hit both sides by the inverse of tangent to get rid of the tangent and get to this basic 3x equals, and root 3 is pi over 3. What I'm going to do now is the unit circle. So from here, unit circle, in this case unit egg or something, not a circle, whatever. Tangent is positive and it's tangent, so pi over 3. So we had this situation before already. So we have a pi over 3 and 4 pi over 3. That's when the tangent is positive in quadrants 1 and 3. Reference angle is pi over 3. Here's my reference angle here of pi over 3 and reference angle here of pi over 3 to give me these basic solutions. So now I have the world of 3x equals pi over 3, and I also have a world of 3x equals 4 pi over 3. So these are the two separate worlds. The next question is the new period. And if you remember, Friday period was pi over b, so in our case pi over 3 is the period now, because it's 2 pi over b for sine and cosine, and pi over b for tangent, cotangent. So now what do I have? I have x equals pi over 9 is the first solution. X equals pi over 9 plus pi over 3 for the second solution. And pi over 9 plus 2 pi over 3, that's 2 periods added. And that gives me the first 3 solutions. Now on the other side, x equals 4 pi over 9. X equals 4 pi over 9 plus pi over 3. And x equals 4 pi over 9 plus 2 pi over 3, which is 2 periods. So this is 4 pi over 3 over here, 4 pi over 9 times 3, 6, 7 pi over 9. Then we have over here 4 pi over 9, and then pi, so that's times 2, no, times 3, 7 pi over 9, and 4 pi, so that's times 3, 9, 6, 13 pi over 9. We see some repetition, but then we're getting the same solution. So what do we have? Pi over 9, 4 pi over 9, 7 pi over 9, and 13 pi over 9 on 0 to 2 pi. I'll explain this problem from scratch, and we have time for another one, I guess. We start with tangent 3x equal root 3, and we apply inverse tangent to both sides, and we get 3x equals to pi over 3. Now we ignore the fact that it's 3x. We draw the unit circle because we need pi over 3 reference angles. Tangent was positive, so quadrants 1 and 3. And pi over 3 reference angles, so we got pi over 3 and 4 pi over 3. So we have our first equation, which gives us the first set over here. And this second set is obtained by the unit circle. We looked at the unit circle, we found this guy, and we replaced pi over 3 by 4 pi over 3, which is, as you can see, this equation and that equation is the same thing. So now we solve the first set independently, second set independently, and make sure that we know that the new period between the adjacent solutions is pi over 3. So we start here. We add to each solution, we add the new period. And we go from there. So repetition I mean, in solutions is possible, and we calculate, we just write the set of all possible solutions. Now you can write infinite set plus n pi, plus minus n pi on each one of these. All right, let's see if they have anything interesting here. All right, so these are some scary questions. I remember I lost 3 points, I believe, when I took the class. I never forget problems like this. Sine 2x equals sine x. Right, it's equation. Solve for x, right? It's problem 70. Well, we have our trig identity for double angle. 2 sine x cosine x is equal to sine x. Now, where did I lose points? I divided both sides by sine x and canceled sine, and you can't do that because you can't divide by sine x. Sine x can be 0. The thing that you are supposed to do when you have these types of equations is to subtract sine x and then factor it. And now when you use zero product property, you have two equations to solve. Now they're both luckily easy equations, but this was the trick. Now for sine equals 0, sine is 0 at every pi. It's 0 at, right, when you go and look at the sine graph. Where's the big one? There it is. You see that sine is 0 at origin, and then at pi, and then at 2 pi, and then at 3 pi. So every n pi, sine is 0 every n pi. So that's easy part to solve, right? Every n pi, sine is always 0. On the other side, we have cosine x equals to positive 1/2. Again, in the unit circle, all students take calculus. Cosine is positive in these two quadrants, and cosine is 1/2 at pi over 6. So it's these two puppies. So x is equal to pi over 6 and 11 pi over 6. So now to list all of the infinite solutions, x equals n pi, x equals pi over 6, x equals pi over 6 plus 2n pi, and x equals 11 pi over 6 plus 2n pi, and this n is 0, 1. Ooh, I need to put plus minus now, because I didn't put the plus minus in the formula. Actually, I could. Let's put in a formula, so it's easier. Plus minus n pi over here. Infinitely many solutions for all of these. You have two separate lines. You can actually check. You can pick a random solution. Let's pick. So check. Pick third solution from x equals 11 pi over 6 plus minus 2n pi. So the third solution is n equals 2. So x equals 11 pi over 6 plus 4 pi, which is 11 pi over 6 plus 24 pi over 6, which is 35 pi over 6. That's what we have. And that needs to work in our equation sine 2x equals sine x. So sine 2 times 35 pi over 6 needs to be equal as sine of 35 pi over 6. I need this to be the same. So you can check your answers by simply plugging stuff in. And now, on the left-hand side, sine 2x and 6 cancel, so you just have a 35 pi over 3. And on the right, you have sine of 35 pi over 6. And they need to give you the same answer. If they're so, you compute, and you compute by what we know from before. Peel off the extra revolutions, so divide this by 6, right? And then do the same thing over here. You divide by 12, and then they have to work out. So 35 divided by 6 is 5. That's 30. The remainder is 5. So this is the same as sine of 5 pi over 3. And 5 pi over 3 is here. So it's a negative answer. Sine pi over 3 is negative root 3 over 2. So the second one better come up with the same answer. So we divide 12 into 35. We get 2 for 24. And we are left with 11. So this is the same as 11 pi over 6. So R11. So this is sine of 11 pi over 6. And on the unit circle, where is the 11 pi over 6? It's right here. Oh, but that gives us negative half. Something went wrong somewhere. We can't have negative root 3 over 2 equal to negative half. That makes no sense. Oh, come on! It ruined everything I wrote. Wow. Hey, well, we're done. Oh. I just one of those glitches with so I have to fix all of this stuff. I'll have to figure out what happened here. We'll talk about it tomorrow. Now I have to go back and fix this so I can email the notes. So I'll see you guys tomorrow at 9. I gotta go redo this now. See you tomorrow. Oh, hold on. I have to take I forgot about the